Kia ora, fellow AWS enthusiasts. Welcome to this AWS Community Day presentation. A big thanks to AWS heroes who have put this on and have allowed me to talk to you today. My name is Terence White, and I'm the Enterprise Platforms Manager at Land Information New Zealand. This means I look after the people who look after the cloud platforms our exciting projects are deploying onto. I've been using AWS for over 4 years and have 8 of the AWS certifications under my belt. Today I'm going to tell you about one of the projects that we've recently released onto our AWS platform that I'm particularly proud of, the New Zealand Basemaps. But first, just a little bit about what Land Information New Zealand, or LINZ as we're known, does. We're the government department that's in charge of the register of who owns what bit of land in New Zealand, and we manage the reference points for the boundaries of the land. We produce maps and charts, we look after government-owned land, and we support the government ministers who need to make decisions about foreign purchases of major New Zealand assets. So what are New Zealand basemaps? Well, territorial authorities like the district councils around New Zealand pay contractors to fly aeroplanes over their districts and take photos with a high-resolution camera pointing downwards. They use these photos for district planning and other nefarious purposes. When they're finished with them, they can give us a copy of these photos, since they're digital, and we put them into our data lake in AWS S3, alongside the photos from other councils. So the Basemaps project is taking these photos and turning them into high-resolution map background tiles. And where we don't have enough photos, or we have a gap in coverage, we're supplementing the data using less detailed photos from satellites. We're making these map tiles available online for free to anyone who wants to browse New Zealand using a web front end similar to Google Maps, satellite view, and to developers who want to put their own product together, like a mobile app or a GIS product that needs a detailed map background of New Zealand. We've released our product with aerial imagery, but we have other base maps with topographic features like roads, building outlines, and street numbers on our roadmap. No pun there. We're also publishing the source code for the project on GitHub for anyone to use for their own education or mapping project, and our devs are happy to engage with other developers around this product. Here's a couple of examples from the web app. On the left, I've focused on to my house. And from the shadows, I'd guess the original photo was taken around noon, and it looks like I had a visitor over. On the right, I started zooming into Auckland and I found something probably a bit more familiar to the audience, Eden Park Sports Ground. So you may already have guessed that we're dealing with pretty large amounts of pretty big photos. And TIFF files might be great for long-term archival storage, but the point of this project is to return map tiles whose coordinates won't align to the TIFF files directly to users as quickly as possible. So we can take as much time to prepare the data as we need, but once the map tiles are live, we aim to return 99% of tile requests within 900 milliseconds. And we know users will be requesting tens to hundreds of tiles in parallel each. To make it easier for the output tile process, we use the Geospatial Data Abstraction Library, or GDAL, to combine TIFF files into larger images, and then compress these larger images using the WebP lossy image compression format developed by Google with a 90% quality setting. Now, this reduces the currently 17 terabytes of data in our data lake down to under 1 terabyte in the Basemaps image cache. We also use GDAL to extract some metadata from the TIFF files, as we want to make sure that we correctly attribute the source or sources of the output tiles, and we need to know the location of the photos for producing tiles later. This metadata is stored in an Amazon DynamoDB table, so we can meet the scalability needs of the service. We're talking to regional authorities about bringing historical data sets in, which will allow users to compare a particular area over time but which will also increase our input data tremendously. So on the left here is a diagram of the image import process, which might help you visualize it a bit better. The images are only imported into our system after they've passed a basic QA sanity check by our staff. The red squares show the larger cache images that we produce from the multiple TIFFs. We run GDAL inside a Docker container and use AWS Batch to run many containers at once on Amazon Elastic Container Service, or ECS, on EC2 instances. We use Python scripts to orchestrate the process and to schedule the processing jobs inside AWS Batch. The EC2 instances are spun up to run the containers, which do the processing, which is actually fairly simple, and then terminated to save costs when there's no more work for them to do. In the picture on the right, we have an overlay of the files we've received for the Wellington City urban region, just to give you an idea of how many TIFF files we receive at once and the scale of the processing that we need to do for each distinct data set. Since we don't generally need the processing to happen super urgently, we tell AWS Batch to use Spot instances. For those who don't know AWS Spot, it allows you to run workloads on AWS when there is spare capacity, like at weekends or in the evenings, at a fraction of the price of on-demand. We set a fairly low spot price threshold, which allows us to make quite a bit of savings. The processing is primarily compute-driven rather than memory or I/O, so we use the C5 family, and we'll be looking to see if we can move to the C6G family if all the software we use is compatible with the new AWS Graviton ARM processors. We're running many Docker containers at a time on the instances, so we use the 9x large instance type, which gives us 36 vCPUs and 72 gigs of RAM. And it makes calculations for the batch scripts which orchestrate the processes easier. Up on the screen, we've got an example of where we did some processing, and the total cost was under $50 for 70 of these large virtual machines, which ran for just about an hour each. If we had to purchase a similarly spec'd server to give us the same amount of processing power in our own data center, there's no way it would cost any less than 1,000 times that, and we still have all the other costs of feeding and watering the server as well to account for. Right, so now we've got a whole lot of processed images in the cache in S3. The question comes down to how do we serve them as map tiles, and how do we serve this to the potentially millions of users requesting potentially hundreds of tiles at a time, and do it quickly enough at scale that they don't have a bad user experience, give up, and move away to another product. And once again, AWS comes to the rescue. I'll walk you through the process of a single user requesting a single tile. The process of requesting the many tiles needed to fill a desktop screen in a web browser is exactly the same, but done in parallel to maximize the network bandwidth. So the tile request will go to an Amazon CloudFront distribution. CloudFront is Amazon's content delivery network, or CDN, and provides a caching layer at many more locations around the world than AWS has regions. A big shout out to AWS for recently bringing CloudFront to New Zealand. That's reduced our network latency by more than half. There's a Lambda at Edge running in CloudFront, which checks the user's API key, if they've passed one through, against the DynamoDB table, so we can keep track of who's using our system. If CloudFront has the tile in the cache, it'll return it to the user directly. If the user is requesting a tile not in the cache, then CloudFront connects through the congestion-free, high-speed dedicated Amazon network to the tile Lambda sitting in our AWS account in the Sydney region. In theory, this will check to see if we have already cached the tile in an S3 bucket and return it if we do. If we don't, then the tile Lambda will create the tile by combining parts of images as needed from the processed image cache and the metadata database we created earlier, and store it in an S3 bucket tile cache for future use, and then return it. In practice, we've found that the creation of the tile is so quick that we don't need to cache it in S3. We haven't implemented the intermediate delivery cache yet. We'll keep that in our back pocket as a future performance enhancement if we need it later. By using AWS Lambda function as a service, this solution will effectively scale itself up and down to meet demand. No intervention on our side. We also don't have any servers that we need to maintain. Does it work well? I think it does. As you can see from this graph, we were serving well under 100,000 tiles an hour on a Friday evening in early September. And then we got featured in an article on NewsHub, one of New Zealand's widely viewed news websites, which later resulted in someone posting a "Hello fellow Redditors, look at this cool thing" link in the /r/New Zealand subreddit. Both of these actions caused immense spikes in traffic to our site. We served over 350 times the usual amount of tiles per hour in the 2 peaks, with a total of well over 50 million tiles over the 2 days of the weekend. The CloudFront cache was able to return 60% of the tile requests directly, and of the remaining 40% that were generated, we were able to return 95% of them within 300 milliseconds, which well exceeds our SLA. The tile generation Lambda was able to scale up to meet the demand automatically and then scale back down again as demand tailed off. No users reported problems with tile delivery. Our admins didn't even know about this until they got in on Monday after the weekend, checked the logs, and then had to go and do some digging to find out what had happened. I'll switch over quickly and give you a live demonstration of the product. So this is the Basemaps front-end website, and I can move it around, and it's pulling those ocean tiles from our server, and I can zoom it in. I'm going to roll the mouse wheel over the Wellington region here, and as you can see, it's pretty quick, pretty seamless, and it's pulling those tiles in from our CloudFront cache on demand. Oh, I see something I recognize in Wellington. Sports stadium. And if I zoom right in, doesn't look like there's a sports match going on there. I think they're preparing for a concert or something like that. Right, so this is a tribute to all those maps out in the world that don't feature New Zealand. We, in fact, have a map that only features New Zealand. If you zoom out far enough on the product, you'll see that we do have a lot of the ocean details, but all the other continents and places are blank. Well, thank you very much for allowing me to present on the technology running on AWS behind the New Zealand Basemaps product to you. I hope you found it both educational and interesting. If you want to find out more about the product itself, you can go to the top URL. And if you want to try the web app front end, have a bit of a play around like I did, head to basemaps.linz.govt.nz. All source code for the product is available to the public in the GitHub repository lins/basemaps. We're using the AWS CDK, so there might be some interesting things in there. To get an API key that you can use in your own development projects, or to get any further information about the product from the support team, please send an email to basemaps@linz.govt.nz. For Land Information New Zealand, I'm Terence White, and I'll now be answering any questions you might have about this.